Good morning, friends. My name is Pavan Mehta, and today we'll learn about the simulation of full bridge inverter with sinusoidal pulse width modulation. As we know, friends, that for simulating the full bridge inverter, this is the circuit of the full bridge inverter. To simulate this kind of circuit, we require 4 IGBTs, 1, 2, 3, and 4. In the first half cycle, these 2 IGBTs will operate simultaneously. That means that the direction of the current will be like this. The first from the current will pass to the IGBT 1, then the load, and from the IGBT 2, and it will get back to the source. In the second half cycle, the direction of the current from the IGBT 3, then the load, and then IGBT 4, and it will get back to the source. In both the half cycles, the current cycle across the load will be opposite to each other, and in this way we are getting from DC to AC. For the full bridge inverter, for the sinusoidal pulse width modulation, there are the 2 possible techniques. That is the unipolar technique, and one is the bipolar technique. In the bipolar technique, we require one carrier wave, that is the triangular wave, and second one is our modulating signal, that is the sine wave. The sine wave frequency will be of the 50 Hz, and triangular carrier wave frequency will be minimum should be minimum 3 times or 4 times of the our modulating signal, that is the sine wave. That means if we have selected 50 Hz of our sine wave, that means the minimum frequency of the carrier it should be, that is the 1100, that means 1000 or 1100 or 1500, that like. These are the 2 pulses that has been generated by comparing these 2 waveforms. This is the pulse train 1, and this is the knot of that pulse train, right? So this pulse are to be given to the switch 1 and switch 2, right? The knot of the switch 1 is given to the switch 4, and knot of the switch 2 it is given to the switch number 3, right? In that case, and we will get this kind of output voltage waveform, the phase output voltage waveform. And in case of the unipolar pulse width modulation, this is the situation. There are the 2 sinusoidal waveforms with 180-degree out of phase shift, and it is compared with a triangular, that is the carrier wave. Now in this case we'll get 2 pulses, right? In this case we'll get the 2 pulses. The pulse number 1 is to be given to the switch 1, and the knot of that pulse is given to the switch number 2. The pulse number 2 is given to the switch number 3, and knot of the pulse number 2 is given to the switch number 2. So in this way we'll get the output voltage waveform like this, right? So now we'll switch to the simulation software to simulate this circuit, right? So we are going to the simulation software. We are taking a new Simulink model. So in new Simulink model, we'll select the new file. So we'll select the blank model, and from the blank model we'll go to the Simulink library browser, and we'll take all the necessary components that specialized technologies, fundamental blocks. So first of all we require the electrical source, so DC voltage source, right? From the DC voltage source, then we require the IGBTs as our switching devices. So from we'll take IGBT with anti-parallel diode, right? Now we require the load, so from the element we'll take the series RLC branch to make the load. So measure the voltage and current, output voltage and current waveform. We'll select voltage measurement and current measurement blocks, right? Now as we see that now we require to make the pulses, gate pulses, right? To make the gate pulses we require, let's say an example, we are plotting first of all the bipolar modulation technique, so we require one sine and one triangle wave. So we'll go to the library browser first of all, so library browser, and we'll take source, so one sinusoidal waveform, one sine wave, and one triangle that we'll take, and one triangle, right? Now to compare these two waveforms we require the relational operator to compare. To make the NOT operation of the pulse we require logical operator, right? And we'll see the comparison of the sine and triangle through the multiplexer mux. And to view all the kind of waveforms we require the scope, so we'll take the scope, right? And all kinds of power electronic simulation requires power GUI block. To simulate all kind of power electronic simulation we'll take the power GUI block, right? Now to avoid the messy look, we'll take go to and from block to give the pulses instead of snatching the wires from pulse generators from here to here. We are directly giving to the go to and from block, right? Now we'll connect all the pulses, all the blocks, sine wave, this is our comparator, this is our triangular, right? Now we'll compare these two, so we'll give this and this. We can see the frequency of the triangular is 1 kilohertz, right? And the frequency of the sine wave should be 50 hertz, and amplitude we are taking as our modulation index as 0.8, and frequency in radian per second, so 2 pi into 50. Okay, so now these two are compared. The output of these pulses are given to the go to block, and the NOT of that, so NOT of that is pulses are given to the second go to block, that name we are giving as B. This is the B. Okay, now friends, our pulses are ready. We can say that we have made our control circuit. Now we'll go to our power circuit. Now to make our power circuit we require 4 IGBTs, so we'll copy these are our 4 IGBTs, right? We'll connect those IGBTs, right, with the source. So we have connected all the IGBTs, right? Now for temporarily we are taking only R kind of load, right? So this is the R kind of load, and we can also measure from the current measurement. Current measurement is to be connected in series with R load, right? And we are connected current measurement in series. The voltage measurement is also connected now. So our power circuit is also ready, right? We are double clicking on the scope to view the both voltage and current waveform simultaneously. We are taking the 2 inputs of the scope, so 2 inputs at the scope, apply and OK. And first one is the voltage and second one is the current, right? And to view this, we can triangle and sine. It will show the comparison of the waveform, that which comparison is to be done. So configuration parameter 1, okay, and done. So it is given over here. Okay friends, now So we are giving now pulses, so this A is given over here and also here. Take the scope little bit upper. So these are the pulses A and A, it will be given over here and here. Now B, so B is not of this switches or not of these pulses, so it is to be given over here and here. Okay, now first of all we'll save this file before run. So we'll save SinglePhase SPWM inverter. Right now I am saving it on the desktop. Okay, so friends, you can see that in both the circuits, first of all we'll change the solver. Friends, you can select any of the solver to solve this circuit, and I have made is discrete. Okay, right friends, we can see that the power circuit for the both configuration will remain same. Either we are simulating the unipolar or we are simulating the bipolar, the power circuit will remain same, right? So we just need to make the separate pulses for the inverter, not to change the entire power circuit. Right, now we run our circuit 0.06. That's an example for the 3 cycles, right? So we are running. Okay friend, see students, this is the output voltage waveform and this is our output current waveform. Right, now to view the total harmonic of the output voltage waveform, first of all we'll load all the data to the workspace, and again we are running the simulation. Now we are going to the FFT analysis to view the harmonic components. Right, see here, this is our output voltage waveform. You can select this is input number 2. Input number 2 is the current waveform. Scope data is the name of our scope, right? And this is the signal number 1. Our start time is 0, right? Number of cycles, that means for how many cycles you want to measure your total harmonic distortion. That means for, let's say an example, we are measuring for the 2 cycles and our fundamental frequency is 50 Hertz, right? And this is the maximum frequency. Students, what the meaning of the FFT analysis, fast Fourier transform, and the total harmonic distortion we are measuring through this graph. It is the graph between magnitude of the fundamental, that means it will show the percentage magnitude of the fundamental, right? And the x-axis will show the frequency, that means how much frequency component are involved in our output voltage waveform, right? That is the, rather than the fundamental frequency represented as harmonic frequencies, right? So from 0 to 1000 Hertz we can see, let's say an example, we have made it 10,000. That means we are seeing the up to the 10,000 Hertz frequency components in the our output voltage waveform from display. So this is the spectrum of the our harmonic. See friends, this is the just analysis that we are doing. We can change the this harmonic spectrum. This we can reduce the harmonics by changing the switching pattern. We can change the switching frequencies, right? So how to reduce all the harmonic components. See here, this is the comparison of unipolar, sorry, bipolar. See friends, this is our triangular waveform and this is our sinusoidal waveform, modulation and carrier waves. Right, now for the simulating the unipolar sinusoidal PWM technique, the power circuit will remain same. As I said, the power circuit will remain same. We just need to change the control. So we are just copying this because this much of amount of control will also same. We just need to add one more sine wave. So here is one more sine wave. We are making over here the multiplexer input is 3. We are giving the input, and we need one more comparator, right? The comparator input of triangular and sine wave, right? Now we just, and we also require one knot, so we'll take the knot, right? The input of first is given over here. This is second pulses, these are the third, and knot of that is as representative of the fourth pulses, right? Now we are giving the name. A and B is already given, so C, here it's a D, here we are give the name of E, and here we can give the name as F. C, D, E and F. So similarly we need to change over here also. The pulse that is given over here, his name is C. The knot is D. The knot of C is D. So we have D, right? Here we'll give the E, and knot of that is given as F. So F, right? Now just we need to run the simulation, right? We can see the comparison block, sorry, the second sine wave must be the phase difference with pi. So we forgot to make over here a pi, so this is the pi, and now we again run the simulation, right? So here it is the comparison, the compared sine wave with triangle. These are the two 180-degree out of phase shift sine wave, that is our modulating signals or reference signals, and this is our carrier signal, that is our triangle, right? So now we see the output voltage waveform. See friends, this is our output voltage waveform of sine wave. Now we can also check the harmonic components of this output voltage waveform, right? So we go to the again FFT block, FFT analysis, refresh it, right? So all the same data will be same, right? And display. So here is the component, total THD component in the output voltage waveform, right? So this is the THD graph of the output voltage waveform that we are getting, right? So similarly we can simulate this circuit with different PWM techniques. Right now it is simulated with bipolar and unipolar output voltage waveform, right? You have seen this is our one configuration scheme, that is bipolar and unipolar, right? We are simulating it for the one cycle, 0.02 seconds, that means 20 millisecond, right? So you can visualize both at simultaneously, both voltage waveforms simultaneously. See, we have simulated this too, right? So similarly we can simulate other PWM techniques with other PWM techniques, and we can also check the THD component for different PWM techniques, right? So for friends, for right now it is up to here only. From the next lecture we'll learn about the three-phase inverter and its PWM techniques, right? Please like, share video. Thank you.